Is multiplication repeated addition? Well, it can be, but it's not just repeated addition. That was part one. Exponents are more than just repeated multiplication. They connect multiplication with addition. Great. But with all due respect to the slide rule and with all due respect to part two, it seems like we're missing something. Maybe we should just say that exponential functions are proportional to their own derivative. And leave it at that, confusing as it might be, and we are a long way from counting apples, unless you've got an exponentially expanding population of apple trees. But we've had fun. We've taken this observation and found a solution which is non-obvious. And we define the natural logarithm, an exponential's inverse function, which doesn't quite work, because it insists on a positive big gamma. Your calculator, however, is more open-minded. But not that open-minded. Wait, I've seen this. I've seen this before. This is I. The square root of -1. I know this. -2 squared, that's 4. So the answer here is 4i. I got this. 4i. Which is a totally different type of imaginary fruit. In this example here, Owl has 3 real apples and Tiger has 4 imaginary apples. Notice they really don't have 7 of anything. So it's weird, okay, but it's really not that complicated. I equals the square root of -1. I got this, or maybe I don't. If your goal was to make me feel bad about things that I thought I understood, well, mission accomplished. I don't know what's worse, the negatives or the fractions. Let's take a look at it. In this case, y equals -2 to the x power. All right. My calculator can give me these values, but for I plug any non-integer x into my calculator, and all it gives me is an error. Let's graph these guys, right? Here we go. 1, 2, 3, 4, 5, 6, 7. Everything in between these dots is an error. And this is weird. It's like a coiled snake that spends most of its time in a hidden realm. And then, when x is an integer, it strikes. Here's a simpler function. Y equals -1 to the x. No change in magnitude here, just positive, negative, up, down, and everything in between is error. It's a blinking light. Positive and negative apples in black. And the key point here is that I'm not lazy. I'm not lazy for not connecting the dots. They really don't connect. They blink. But if they did connect, the cosine function would be convenient. I'm just saying that, and we'll do sine and cosine stuff later, so memorize all these special angles for now. Back now to the weird on-off function. Hello, friends! He's gone. He's back. Gone. Over there. Over here. What? It's like he's on this giant big circle that takes him in and out of the universe and back. Time to get to equations, and we'll have some good ones, I promise you, and we'll need them because this guy needs to be solved, generally speaking. Euler's equation, we'll prove this in part 4 or part 5. Not quite sure yet, but I hope you've seen Euler's equation before. This guy, maybe, however, you have not seen, but to us, he's almost as important to us, he or she. So important that I'll mention what this equation is not. This thing is cool in its own way, I guess, but it's not what we're talking about. We're talking about something much weirder, because this over here on the left, this doesn't exist, and neither does that. But the natural logarithm does exist. It turns multiplication into addition, which is exactly the point. Right? Wrong! That was a test. Wrong! I did something wrong. See, there's a problem. Caution. Danger. There we go. But now, since the natural logarithm of -1 does not exist, we'll name it sigma. Something to hold on to. And since sigma doesn't exist, we'll call it real number tau times I. E to the I tau equals -1. Sounds familiar? Hey, Euler, get over here. We want cosine tau to give us -1. And we want sine tau to give us 0. So 0i and -1. And when does that happen? Only at the angle pi. Well, not only at the angle pi. This thing could go on forever. But we're good. Sigma, you know, natural logarithm of -1. You know, it's I tau. Sigma is I pi. So hand me back that other equation and we are out of here. And if you feel like I've just restated Euler's equation in a different form, that is not my problem. This is my problem. Or more generally this. Can we solve it now? Well, my calculator can. Sometimes, but only when x is an integer. And if this is hard to read, I'm sorry, but it works. And I think I can fill in another couple rows, see what I mean in that. But for the rest of them, we're stuck. Let us then restate this with e and the natural logarithm, which allows us to say this, which is kind of our definition, which means it's the hardest thing to see. The definitions are the toughest. Does this help? So I see how you are. You're telling me that exponents are not repeated multiplication unless you want them to be repeated multiplication, and then you allow it. I see how you're doing this. All I'm saying, if you buy this and you buy them, we can get started. 1, 2, distribute, page up, break apart, rewrite, oil it up, solid bronze, golden delicious. Let's do it. Little help. Gross. Let's clean it up. No, wait, it's not gross. It's not gross. I'll explain it later, but this is what we want. This is not gross. Embrace the messy. All right, we're done embracing the messy. Clean it up, a solution and an equation, but what does it mean? It means the owl is going to eat or lose about 1.5 apples, and the tiger is going to gain the same number of imaginary apples. And the fact that the magnitudes here is the same is just a coincidence or a special choice, but here's another problem and another solution, but I like this one better. It has a magnitude and a direction. More on that later. First, we have a grid to fill. No one can tell me I'm wrong because no one can read my work. Ha ha! Hey, there's that guy. And if you could read it, you'd notice symmetry across the rows, something I called angle. The magnitude depends on gamma and on x, but the angle depends only on the exponent x, right guys? One more thing, we're not just x and y, real and imaginary. And this problem has a solution, a point on the real imaginary plane, a magnitude and a direction. Same with every other solution. Let's rewrite those angles in a more familiar way. That okay with you guys? The calculator only gave us these answers, the real ones. Knowing a little bit about I gave us these answers, the imaginary ones, the purely imaginary ones. The complex answers were golden delicious, and we are totally done. Totally done getting started. Addition is a slide, multiplication is a stretch, exponents are time-consuming, and we like to rewrite gamma, which was a problem earlier in a past life because we had a problem in a past life with big gamma being negative. That's no longer a problem. Negatives and exponents just mean imaginary numbers, and we're good, except that we don't know what exponents do. They are proportional to their own derivative. They change slope. Here's a car speeding up, vroom. Here's a car slowing towards a stop. Erk. And that's all there is. Speeding up and slowing down. I mean, can a number change if it's not getting bigger or smaller? Can a car's velocity change if it doesn't change speed? Yes! If it changes direction, it can go in this circle forever. Exponents can rotate you. Recognize these imaginary velocities? They have the same magnitude but different directions. Addition slides, multiplication stretches, and exponents rotate, but they do more than that. And it all starts with counting apples. Sell enough of them and you can buy a house. Put that house in the wrong spot and you might need to nudge it a little bit to the right or to the left. Get good at nudging and you might find yourself nudging it by only ½ an inch. Now my odd sounding claim here is that addition discovered fractions. Of course they were always there, but you skipped right over them, didn't you? You could count 10 apples and you would skip right over the number 7.6, like it wasn't even there. As your family changes, your house might need to stretch or squish. My odd sounding claim here is that multiplication discovered the irrational numbers. I need to double my house. To do this, I will apply the stretching operation beta, and then do it again. Got it? So the challenge here is to find the ratio y over x. Again, you do beta twice and you'll double the size of the house, but what is the ratio of y over x after we just do beta once? That's what I want to find out, and I want a good, proper ratio here, a simple, relatively prime. No way I want x and y to both be even. I want a good, proper, simplified ratio. Okay? Well, I don't know about x, but it appears here that y has to be even. That has to be true if y squared is even, but if y is even, then it's equal to 2z, but in that case, x also has to be even, and I said they couldn't both be even, so the ratio of y to x doesn't exist. Multiplication discovered irrational numbers. That's something you would never get if all you were doing all day was adding fractions. A kid is taking a fraction adding test, and the kid says this is impossible. Well, he or she probably doesn't realize all the holes in the number line. Those values, those places on the number line that you will never get to. You will never touch them with any fraction. Exponents rotate, of course, as we've described at great length here, and they need imaginary numbers to do it.